Good afternoon, everyone. Welcome to Economics and Best Practices of Running AI/ML Workloads on Kubernetes. My name is Malin Patel. I am a product manager at Google Cloud, and I'm pleased to introduce our co-presenter, Yaron.
Hi, I'm Yaron. I'm a co-founder and CTO for Iguazio, a machine learning platform company.
Thank you, Yaron. Today, we are going to talk about two hot topics in computer industry. First is Kubernetes, and the second is AI/ML, artificial intelligence and machine learning. Both are critical pillars of modern computing environment. In today's digital economy, data is the new currency. For many of us, data is the lifeblood of our company, and we want to convert the data into meaningful information. AI/ML is the engine which helps us convert the data into meaningful information. And with meaningful information, we can drive better business decisions and take actions. Industries across the world are heavily investing in AI/ML capabilities. So as a community interested in AI/ML, how can we make AI/ML simple, fast, and cost-effective? We want to make AI/ML simple so it's accessible to everyone in our organization. We want to make it fast so you can train the model fast, get insight faster, and drive business decisions faster. We want to make it cost-effective in order to democratize AI/ML so that it's accessible to everyone. So when we think of AI/ML, we typically think about model building and model training. However, we need to realize that AI/ML is much bigger than that. ML is typically a small part of an end-to-end AI/ML application. A lot of skills are needed to build an AI/ML application. For example, a data engineer may cleanse the data. Another engineer may extract features. Data scientists may build models. An application engineer may convert the model into an API. And finally, an end user may use the applications which are built using those API. So how can we make AI/ML teams 10x more productive? How can we give them an environment so that they can innovate faster? That's why we need cloud-native AI/ML platform. Kubernetes has become the de facto standard for cloud-native computing, and we want to bring the power of Kubernetes to AI/ML. Kubernetes makes AI/ML workloads scalable, portable, and composable. With the help of Kubernetes, data scientists can focus more on building and training models instead of worrying about underlying infrastructure. All they have to do is choose your favorite ML workflow framework, pack the models up in Kubernetes, and run them on Kubernetes at scale. Kubernetes takes care of scaling the workload from a single node to thousands of nodes. It makes data scientists more productive. So why Kubernetes for AI/ML? Kubernetes provides 3 core features that are very attractive for AI/ML workloads. The first is portability. Kubernetes provides cloud-native, open, and standardized APIs. By using Kubernetes, you can seamlessly port your workload from your laptop to your cloud to your private data center. Second is scalability. With the help of Kubernetes, you can scale your ML workload from a single node to thousands of nodes. Kubernetes also supports hardware accelerators such as GPU, TPU, and also auto-provisioning and auto-scaling, which makes scaling your workload simple and easy. And the third is productivity. Kubernetes makes data scientists and data engineers more productive by freeing them up from managing their own workstation servers or VMs. It lets you focus on your model building and model training instead of focusing in managing VMs. So the Kubernetes is actually application agnostic. So Kubernetes provides many, many advanced features like scalability, load balancing, scaling, etc. However, it does not know anything about ML. This leaves a lot of work for ML operations teams in setting up the infrastructure, downloading and installing ML frameworks and libraries. Kubeflow fills that gap. Kubeflow is actually a Kubernetes native open source platform to develop, deploy, and manage portable and scalable machine learning workloads. Kubeflow provides higher-level abstractions, such as TensorFlow job, which makes running TensorFlow job or training job much simpler and easier on Kubernetes. It integrates TensorFlow distributed training and estimator APIs with the Kubernetes. It uses Kubernetes to scale training and leverages hardware accelerators, and it benefits from auto-scaling and auto-provisioning capabilities of Kubernetes. And with this, you can also benefit from the vibrant ecosystem of Kubernetes toolchain to develop your ML workflows and run ML workloads. Kubeflow also provides advanced abstraction for serving. So imagine that you build a very advanced model for movie recommendation. Now you want to test this model on a small scale with a global traffic to study the fidelity of your model. So if you deploy this model in US, the traffic will be overwhelmingly from Hollywood movie fans. If you deploy this model in India, the traffic will be overwhelmingly from Bollywood movie fans. So you have a dilemma. On one hand, you want your model to get a slice of traffic from the regions of your interest. On the other hand, you don't want to deploy an experimental model globally to limit the blast radius. Here, Kubernetes and Istio comes to the rescue. With the help of Kubernetes and Istio, you can configure the load balancer so that your model gets a slice of traffic from the region of interest, so you can test the fidelity of your model from the traffic that you are interested in. Also with Kubernetes ecosystem, for example, you can use Prometheus for exporting your model metrics. You can also use Istio for telemetry and traffic splitting. So Kubernetes and Istio make many, many model lifecycle challenges simple and easy to handle. So in ML world, there are two distinct experiences that we have to address. So there is a day zero experience, which is focused on model building, where a hosted notebook can make a huge difference. And once a model is built, then you have to deal with the productionization challenges, where you have to deal with security, scalability, logging, monitoring, etc. So now let's look at how Kubernetes helps to address those challenges. So in day zero, we are interested in building and training models. And data scientists typically train the models using notebooks, and they have their own preferences for the libraries they would like to use and the framework they would like to use. So here, we can benefit from hosted notebooks, which come pre-configured with the most popular libraries and the frameworks. And this includes libraries such as Pandas, NumPy, and many more, and machine learning frameworks like Keras, TensorFlow, XGBoost, etc. So data scientists can open their browser and connect to the notebook, which are hosted, and start fetching the data and building the models directly into the notebook. And they can train the model in the notebook, and the best part is they can deploy those models once they are trained directly onto Kubernetes from the notebooks, which frees them from learning intricacies of Kubernetes. So once a model is built and trained, the next is how do we deploy into production world? Here, we have to address many production-related challenges. For example, security, logging, monitoring, telemetry, also data gravity, and so forth. And as you may all know, because of the variety of challenges, lots of workloads today run in on-prem environment. and challenges related to regulations, latency, data gravity, and so forth. So what that means is a lot of models will be running in on-prem environment as well as in cloud environment. We call it hybrid model. At Google, we are investing heavily in our hybrid strategy. In the hybrid world, what we see is you can run your machine learning workloads in on-prem environment using open source tools like Kubeflow. When you are in a cloud environment, we offer AI platform, which is managed equivalent of Kubeflow from Google, and you can run your models directly onto the AI platform. So AI platform is basically developer environment, integrated developer environment for data scientists and data engineers. In that world, all the pain of doing DevOps is taken care by the Google, versus when you are on-prem, you have to manage Kubeflow on your own. So you can use your favorite notebooks and Python code to talk to Kubeflow on-prem, as well as AI platform on GCP. However, the underlying APIs that are supported on Kubeflow and on AI platform are slightly different. So the Kubeflow supports Kubernetes-style APIs, and AI platform supports RESTful APIs. And often, data scientists use their local environment to run their own code and validate the model. So in that case, data scientists have to deal with many different varieties of APIs. That's not fun. So to address that, we are developing a hybrid machine learning SDK, which basically abstracts away all the intricacies of underlying platform into common set of APIs. We call it Kubeflow Fairing. So what is Kubeflow Fairing? Kubeflow Fairing is an open source hybrid machine learning SDK for data scientists to write ML code once and run anywhere. So not only that, it also gives you the ability to package your data science machine learning workload for remote execution. So it abstracts away the pain of managing different underlying platforms. And now I'll show you some examples. So this chart, you see 3 different ways data scientists have to deal with their platform. They can build their machine learning code locally, or they can build it on AI platform, which is a managed service provided by Google, or on a Kubeflow. If they're developing locally, they can use their favorite Python toolkits, which they are very familiar with. When they develop it on the AI platform, they have to provide basically G-Cloud APIs argument, which basically list all the dependencies and packages that are needed before machine learning code that is developed by data scientists can run on AI platform. If they do the same thing on Kubeflow, they have to write their own YAML files. So this is not fun to deal with all these dependencies which are handled in a different ways. In the Kubeflow Fairing world, all the code is abstracted away into a common code, which almost look identical. The main difference here is the backend definitions, which are provided as an argument to Kubeflow training job, is slightly different in each environment. So as you can see here, the backend definition is local for local environment, AI platform for AI platform environment, and then it's just Kubeflow for Kubeflow environment. It's easy to imagine that this could very well have been a development, staging, and production. The only thing that ML operations team has to do is to basically configure the fairing.config file in order to handle the differences between this environment. But for data scientists, the code looks almost identical. So now let me show you an end-to-end demo how this works. So first, what we will do is we'll discover an existing model from AI Hub. And AI Hub is basically one-stop shop for storing and sharing your AI assets, for example, pipelines, your models, your notebooks, etc. This makes collaboration within an organization much easier. Once we discover the model on the AI Hub, next we'll open it in a hosted environment using Jupyter Notebook, and then we are going to train it in 3 different ways. So now let's go to the demo. Just give me a second. Okay. Looks looks like some. All right. So what you're looking here, we start at the AI Hub search space. And what I'm going to do is I'm going to search for a cancer detection demo. So as soon as I hit the search button, you will find that there are 4 results. 3 of them are actually notebooks, and 1 is actually the model itself. We are interested in the 3rd result, which is a cancer detection model. So we go there, and we open the model in a GCP-hosted notebook. So that's what you're seeing here. So this is the model I'm going to open. So this is how the model looks like. On the top part of the model, you have environmental setup, which is very common. Next, what you see here is basically we are exploring the data. So understand the data and clean the data. After exploration, we will go to basically a visualization. So here you can see some code for the visualization. When we run the visualization code, it will display some images, which are basically positive and negative samples for your cancer detection input. Then we build the model. So after the model is actually built, we want to fetch basically the embeddings, and those embeddings are fetched from the AI Hub for our model. These are image embeddings, and now we are going to train it on 3 different environments. So the first environment is basically local environment. As soon as we start training on local environment, it will start showing us logs. The second environment is Kubeflow environment. Here you can see the backend config, which says Kubeflow. And the third environment is AI platform environment, and the backend config is GCP. So now we will train the local model. So now it's training, and you can see the logs are being displayed. The training gets finished in 184 seconds here, and you can see the loss and accuracy metric. Next, we are going to train the same model in the Kubeflow environment. So in this case, the model gets packaged by Kubeflow Fairing, and it's executed remotely. And the logs are streamed back to the notebook. So in the top part of it, what you see is that the model is actually packaged as a Docker image and is put in the repository from where it gets picked up by the Kubeflow. And then the execution is pretty much same. You can see the logs in the notebook. And the third is we're going to do the same thing in the AI platform training environment. So the key difference that you will see here when we do it in the AI platform environment is now the logs are actually made available to be streamed to Stackdriver. So you can actually, I'll show you in a second, in this case, we provide you a link, so it opens the logging in the Stackdriver, and from there on, you can monitor and do everything that you want to do in the Stackdriver environment. So what this shows here, so this is the link to the Stackdriver, and now you go to Stackdriver and open the logs. Yeah. So the new logs are made available here, and then you can work through your logs in the Stackdriver environment. So now going back to my slides. Okay, so let's quickly review what Kubeflow Fairing provides you. So it's basically, the advantage of Kubeflow Fairing is it's a data scientist focus. It works with the data science friendly environment and notebooks, as well as data science friendly programming languages. It's a multi-platform, so you can seamlessly move across your local environment as well as your GCP environment or your private data center environment. It makes your training and inferencing very cost effective because this allows you to burst into the cloud when you run out of capacity on your private local environment. you can use the Kubeflow fairing for the lifecycle management, and it also supports the multi-frameworks, including XGBoost, TensorFlow, and Python. Okay. So what are the advantages of Kubeflow fairing for MLOps team? So basically, it allows you to enforce your best practices that you want to enforce across your organization. Second is it's open source. So there is no lock-in. You can make use of it right away without having to worry about any vendor lock-in. And also, as I mentioned, with the remote busting, you can save a significant amount of money on your operations cost. So with that, let's move on to the second part of the talk, and I will invite Aaron to take us from here.
Thanks, Marlene. So I have some ambitious demo, and I hope it will work and all that. But before diving into a demo of like a full pipeline using Kubeflow, let's talk about some basics. What I want to show you is essentially how we can build a fully automated machine learning environment and leveraging some of the serverless technologies that are now integrated into Kubeflow. So one of the key challenges today is that machine learning is pretty complicated and siloed. So we have some folks still working on Hadoop and data lakes and Spark and all that on Yarn. Some data scientists that come more from a Python mindset and deep learning, machine learning, scikit-learn, XGBoost, TensorFlow work on sometimes their laptops, sometimes notebooks, sometimes Kubernetes if they're slightly more advanced. And then we have the operational aspects of where do you deploy all that. So you have some containers that come from the machine learning world, and they just present endpoints that get some vectors and process and respond. And you have some other containers that interact with those containers. Now, we have 3 different disciplines, 3 different silos within the organization, and most of the transfer of artifacts and knowledge and everything is done manually today. So we need to change that. So the general idea is why not use Kubernetes as sort of a unified architecture, not necessarily a single cluster. You may still have multiple clusters, but sort of a unified architecture for delivering such a pipeline. So you do need various ways of storage and databases underneath. And then you have all those variety of services that come from those different disciplines. You can run Spark today, not many know. You can just run Spark, Presto, Hive, all those things on Kubernetes today, but you can also run PyTorch, TensorFlow, etc., and other things that are more sort of on the operational side, Prometheus, Grafana, serverless functions, and so on. So what you can build is some pipeline which is slightly more advanced and have 3 components. One is collection of data. Now, most people that come from the data world still think of collection of data as an ETL process. If you're being a slightly more modern application, collection of data is also streams that just feed in or scrapers. You need some weather information. You don't want to store that in your own data lake throughout the entire history. You can just go to an external weather service, external real-time stock trading information service, etc. So you need automation for grabbing data and bringing it into sort of this place where you're processing the data. Second thing that you do once you've brought data and preferably labeled that and prepared that a bit, you need to do machine learning, training, and validation. And also here you can leverage the advantage of Kubernetes in scalability. You don't want to run an experiment on this notebook or this specific VM. You want to be able to run the same experiment or the same training on potentially tens or hundreds of jobs, depending on the size of your task. And you want to pool resources because I still see people just taking a Jupyter, attaching a GPU to that. In Amazon, that's like $12 an hour for a quad node GPU. If you have money, that's okay. But then you're wasting those resources. So the right approach would be to essentially pool the GPU resources, and every time you launch a job, just have a container, mount this GPU, run, and decommission itself. And if you're a group of data scientists, then you can pool those resources. Or if you're using a cloud, you can pay per use for some of those resources. And then the last stage is once you have a model, you want to serve it, and then you can use containers and potentially serverless functions as a way to do serving. Also here, many times people think about serving as something that gets a vector of floating point numbers and respond with the floating point numbers. But then there's a critical challenge here. How do those floating point numbers get generated? That's sort of a dark secret, no one knows. So essentially the real data in the world is geolocations, is customer identifiers, etc. So the first thing you need to do is feature assembly and only then feed it into a model. And last but not least, we have to have sort of a feedback loop. We have to monitor everything that happens during production. And we could use things like Grafana and Prometheus to do that and feed the data back into the pipeline. And the last thing that we want is that essentially the user, the consumers of that platform need some easy way to access this entire system, because there's a lot of complicated things, service meshes, containers, YAMLs. We want to abstract it through notebooks, through pipelines, we'll show that, and through things like serverless functions. So Kubeflow, essentially what it's trying to do is bring all those different projects for all those different tasks within the pipelines under one umbrella with the sort of simpler integration. And this is where you can build a real pipeline. So let's look at what do I mean by real pipeline. So the first thing you need to do is collect data. And the reason I put 3 icons here, again, to make sure people understand that collecting data is not necessarily doing an ETL job from Oracle or reading an S3 Parquet file and loading it into your sort of data science platform. Sometimes loading data is streaming, it's Kafka Stream. Sometimes it's fetching from some API services. Then once we take all that data, we need to create a feature vector, and we prefer to sort of snapshot it, version it. So when we run this experiment again and again, we make sure that we get the same result. So we need to take data, and then we put it into a pipeline. The first step in the pipeline will be to do training. So we need to take some code, some notebook, load it in, run some training, generate an output sort of a data set or model. The second thing we'll do is probably validation. Again, we'll take some code that does validation, run it in, and get some reporting, and so on. Then we do deployment. The deployment generates some artifact, like a container that may be deployed in a different cluster. And once we've done the entire testing, everything works, we may want to get some notifications. So every step in the pipeline has some sort of output result. And this is just the sort of the data science or machine learning pipeline. Sorry, I had another slide, but and this is where we can actually use Kubeflow pipeline. So Kubeflow pipeline is a relatively new component, but very powerful. It allows us to essentially create those dependency graphs with complicated policies. It allows us to view the results, the inputs and the outputs for each experiment, and even compare different results. One very powerful thing I like about Kubeflow pipelines is the ability to componentize elements. So today there are components from Google, from Amazon, from IBM, from Iguazio. So people can just grab components and integrate them into their pipelines. The next thing we need to think about is not just the offline sort of the machine learning pipeline, but also the real-time pipeline or the serving pipeline. And again, a serving pipeline doesn't end with just having a container that does model serving. A serving pipeline includes some application, let's say a web app or a mobile app that brings some data in, and then you need to essentially form this feature vector that is fed into the model. Where is the data coming from? Some of it will come from the event itself. Some of it is from like real-time sources. Some of it from historical sources that also have been used for the training. And then we have the model serving. So you could see all those things always introduce complexity. There are so many moving components that we need to deal with. So what's a simple way to address all this complexity without building Docker files all the time and compiling and manually scaling and manually logging and manually securing? Everything is essentially adopting a serverless approach. So serverless is a great thing. Everyone likes serverless. There was even a serverless day on Monday. And what is serverless really about? Serverless is about automating the process of taking code and operationalizing it, thinking about all the aspects of logging, auto-scaling, forgetting about YAMLs and focusing more about requirement specifications, and also adding all the instrumentation. So one of the key challenges around machine learning and data science is that data scientists are not really used to think about like exception handling and security and all those things. So having more and more automated instrumentation built into the code is actually a good thing, especially when the gap is so big between data scientists and production code. And other things are like auto-scaling, rolling upgrade, etc. But what's the challenge around serverless? That it wasn't designed for data science or machine learning. Okay, what does it mean? Usually single-threaded, no concurrency, no support for GPUs, because that's like hardware, it's a stateful thing. Usually stateless application patterns, so when you need to deal with things that deals with state and context and caches, that's pretty hard to do. Most of the frameworks think of it in terms of HTTP. When you're starting to move to streaming and batch processing, there's state involved and checkpointing and all that that's not really designed to most of the frameworks, and hard debugging and diagnostic. So with that in mind, we came with an open source project called Nucleo. It's already like 2 years on the road, which is very oriented towards data processing, analytics, and machine learning, and I'll show some of those capabilities in a minute. What's different about Nucleo on the lower levels is first, it's extremely high performance. Running your code within Nucleo is faster than running your code without Nucleo. And that's because Nucleo itself deals with real-time performance optimizations, real-time GPU scheduling, real-time thread scheduling, garbage cleaning, all that is handled by the runtime. Second is all the features around data processing, checkpointing, sharding, rebalancing, integration with the NVIDIA Rapids for ETL and machine learning, integration with other frameworks for GPU optimizations, all the different streaming APIs you could think of, Kafka, Kinesis, Google PubSub, Azure Event Hub, MQTT, Jobs, etc., Cron, HTTP. And one thing that I'm going to show, which is very useful, is it's stateful. It actually can work on top of volume mounts and shared, has notion of shared context that can hold things like database connections, GPU resources, etc. Other things that sort of make it more suitable for data science is first, automation around Jupyter. There's an entire project just called Nucleo Jupyter, which is all about how to convert Python code or notebooks automatically into real-time artifacts that contain all the aspects around the function, not just the function itself, but also the resources it's going to consume, dependencies, packages, streaming API, endpoints, etc. The second thing is the integration with Kubeflow pipeline that extend the features of Kubeflow pipeline for doing things like parallel processing steps and code build steps. You can build steps that essentially build the code. I'll show that. Things like stream processing, etc. Also, again, around GPUs, we do a lot of work on GPUs, very close relations with NVIDIA. NVIDIA is using Nucleo across the board in different places. You can actually, this is a benchmark that was done with the Samsung on a specific Samsung commercial application. We're running the same application on Nucleo with GPUs was 4 times faster compared to running it just on container. Part of it is just how Nucleo knows how to manage the queuing for the GPU resources, which is very transparent to the user. Okay, so with that, let's do some demos. Okay, so let's start with a few basics. Before I go, what I want to show you is building a full pipeline, but let's start first by understanding what is Nucleo. I'm using our managed platform, but sort of the open source is exactly the same. There's no difference. So essentially, when you go to Nucleo, you have projects, and within projects, you have functions, and you can create function. This is a simple function that does like NLP. Let me increase the fonts a bit. By the way, it has an embedded VS Code contribution of Microsoft. You're not forced just to work with the embedded code. You can always work from different sources, image, archives, Git repos, zips, all that is supported, so you can embed Nucleo into a CI/CD pipeline. You can configure many different things in Nucleo, all the different resources you know of in Kubernetes, whether it's CPUs, GPUs. It doesn't have to start from zero. In data science or streaming, you don't really want to start from zero. So you can choose what's the range of resources. It can work with any type of Kubernetes resource, like values, secrets, config maps, labels, annotations. You could give it the source image that you want to build on top of it, the function. So it's not like very limited. You can essentially do things like on builds and from builds, and essentially put your entire Docker file into descriptive approach. It has also volume mounts and PVC, so you can mount functions into, you can mount data and storage into functions. The other very interesting thing is the triggering. So essentially not just triggering from HTTP, you can trigger from a Kafka stream. So when you're triggering from a Kafka stream, the Nucleo engine, which is a scale-up, scale-out load balancing engine, will know how to work with all the shards on the stream and will dynamically, if it needs to scale, it checkpoints, rebalances, and you don't lose a single bit during that process. So it allows you to auto-scale streaming, and that's supported across, again, very large variety of triggers, and adding a trigger is very trivial. So there are about 14 triggers right now, and people can just add additional triggers. So that's more on this front. But let's look at it from more of a notebook perspective. I hope I'm on the right one. Okay, so data scientists don't like those sort of UIs that I showed you. They like Jupyter notebooks, and what they'll do, let me show you a simple example. This is the same NLP function that I mentioned before. Get some text, run some processing, and responds, does correction, translation, and sentiment analysis, very few lines of code. So you can essentially put some magic instructions to like pip install, to control environment variables, control all sorts of spec, Nucleo spec elements. I didn't show that, but Nucleo spec is essentially a CRD. If you download or view Nucleo spec, it's essentially a CRD. It's a Kubernetes element. You can do kubectl functions. You'll see that CRD. But again, you could just do all of that. You could test your function locally using the built-in test harness, and you could then just magic deploy, and that will automatically build that function on the cluster. And then once it's done, I can just curl into that function and see that it's working. So taking that, and let's build something more complicated. One of the nice things that we've done recently is the integration with Kubeflow pipeline. So there's an example in the Kubeflow website where you could see a simple example of essentially taking a notebook through a URL, the same notebook I just showed you, running a component of deployment. This component of deployment is essentially loading the notebook, extracting the code as well as the sort of annotations, the magic commands to figure out how to build the container. Based on that, it's building the container, providing me logs, and responding with the endpoint address for that running function. And then the second component is like a Nucleo invoke, which is essentially running test against the container. So if I'm going to run this in a pipeline and just run this code, what I'll see is that the first step of deployment is building a container, pushing the image, doing all of that, and essentially responding with an endpoint. And the response is the invocation response. One thing here that you see is that you haven't seen it, that the environment variable was saying the translation is to French, and I'm actually getting Spanish because I'm in Barcelona, and that's because you can even override parameters when you're doing the deployment. So the code in the notebook can be X, and then I could just replace all sorts of parameters, and that in the deployment time. So with that, let's move into something slightly more sophisticated. So let's assume we want to build a full pipeline. A full pipeline consists of data ingestion, data preparation, training, and then transfer to production. So what I built here is 4 different functions. Okay, like preparation, a generator is essentially simulating a real-time feed. Data preparation is taking that feed and building joins, aggregations, etc. on that data. Training is essentially creating a training model of that thing. It's using, by the way, Dask and Nucleo and Dask and Scikit and sort of an XGBoost. It's not deep learning. So each one of the steps in the pipeline is a scale-out step. None of the steps is sort of a single function. So I can essentially go and take the generator function, which is just a notebook, a lot of instruction because it supports different types of data, like databases like our time series, but also Parquet file. And when I run it, I could just run it locally and just through built-in the test harness that when I'm importing the Nucleo SDK library, it automatically generates a test library. And then what I'll see here is that within the matrix, essentially I got some file. Now one very cool thing I did here in the definition, I said that Nucleo supports mounting, supports shared files. So there's a nice thing in the Nucleo SDK that essentially allows volume teleporting. So I can tell Nucleo that my volume in my notebook is going to be remounted into the function, which is what I did here. So you see that I have my own directory. What I'm going to do now is essentially I'm going to deploy a Nucleo function, and you'll see that the Nucleo function, the real-time Nucleo function will write into my directory, hopefully, if everything works. So essentially now I'm asking Nucleo to deploy. Again, the demo guys will be with me. And it's going to run a deployment. Okay, started. Which, when I'm doing this trick, is essentially taking my notebook, parsing my notebook, optimizing it, extracting all the things that give it configuration, like this volume mount, or, by the way, you see it's done. And now I'm going to run against that endpoint. Okay, I'm done. And what I'm supposed to see if I'm going to refresh. Okay, you see another file. So it's pretty cool. So I essentially took my notebook, convert my notebook into a container, ran it in a different container in the cluster. I gave that container through very simple annotation. I told it, you're going to write into my directory, or my directory is going to be mounted into your container. And it just wrote into, I don't even need to move objects around. You know, I just refresh and I have this data. I can actually go and use some utility I have here to read, Parquet, and sorry, I probably need to import. Oh, I think missed here, so never mind. So essentially, I could just go and read the data, which is on the same place. So with that, then we did something that does deployment. The next thing we want to do is data preparation. So same thing. I want to take those Parquet files. So I have here instructions for Nucleo that I need this container to essentially have all those Python packages. I want it to be based on Python Jessie, and I want this sort of virtual endpoint, virtual mount point, and some credentials, and things for Dask, etc. And then I'm running all this thing. I can run the same code locally, but just running here sort of this handler and this test, and I could do the same deployment from here. And again, when I'll run this thing, let's look at the features. No features. If I'm going to run against the real-time function, I'm supposed to now get features delivered directly to me. And I could do exactly the same thing for the other notebooks. By the way, it's using Dask. Anyone familiar with Dask? Dask is sort of a parallel Python processing library that supports many primitives of data frame, of Pandas data frame, as well as scikit-learn and XGBoost. One of the nice things that we're working with NVIDIA now is support for GPUs. So Dask, cuDF is the sort of equivalent of data frame, and QML is the equivalent of scikit-learn and XGBoost. So I can essentially do the same things around the training. I'll just generate the model. You see, and I'll go to the models directory, and hopefully I'm going to have a model. Good, and then let's do the prediction. So again, same notebook. Now, one of the things that I forgot to mention on the first one, sorry, that you see this is commented out, because in real life I don't want to go and click Shift Enter and do something. I want in real life this generator to actually work in a cron job and every 1 minute go fetch something from an external service or do something. So if I uncomment those two lines, just essentially say nucleo config spec triggers cron with 10 seconds, it's essentially going to add a cron trigger to my function. And my function is actually going to, every second is going to push things. So I don't have to just think about pipelines as something that I have to invoke. I can put things like streams, cron jobs, HTTP endpoints as part of my, my pipeline. So with that, the next thing I want to do is essentially create an automated pipeline, because I'm sort of tired of messing with all those sort of shift enters. So I can essentially write this specific notebook. What it does essentially loads those two components, which are part of the Kubeflow repository. Actually, I only need the invoke one. And then I'm just daisy chaining those different 4 functions all the way from data generation, data preparation, training, and inferencing. Okay, and one just after the other. And then I'm just running this experiment. Okay, so if I'm going to take that notebook and run this experiment again, then supposedly I'm going to see something running here in a second, and all this pipeline that I described that is going to run automatically. Okay, so you see I got the first step running, okay, writing into this directory, and then the second step is running this, and then running the training, and eventually getting the inferencing done. So now if I'm going to go back to my my thing, let's just go to matrix. You see another file was generated a second ago. So essentially what I did, I didn't know anything about YAMLs, nothing about Docker. The only thing I did, I was in my native environment of notebooks. I just put some annotations that's saying, you know what, I really want my volumes to be mounted. Potentially I need a trigger of cron, maybe Kafka. I want a couple of GPUs, and just sort of specifying my requirements. And this is automatically generating scale out processes on my cluster. I can still work on my notebook if I don't want the cluster. But if I want to scale my experiment, I just shift entered on the deploy thing. And if I want to turn it into a recurring process of doing this over and over again in an automated fashion, I just turned into Kubeflow pipeline and created a full pipeline. Okay. One thing that we want to improve, and we're working with Jeremy and people from other companies, is to try and create sort of a metadata management layer within Kubeflow that will simplify greatly those notebooks. So I'm going to share all those notebooks in, probably will pull them into the Kubeflow GitHub so everyone can play with those. Again, they could use any generic resource, and we hopefully going to make them better and better over time. Good, so that's for my demo. Any questions or no questions? Thank you. Yes. Sorry? I'm not sure I heard the question, sorry.
Okay. No, my question is, Kubeflow is going to run on Kubernetes, or it itself is having Kubernetes?
So Kubeflow runs on top of Kubernetes.
Yeah, that's what my question is.
Yes, and Kubeflow, essentially Kubeflow is both, what is Kubeflow? Kubeflow is both a set of components that sort of sit under the same pile, okay? And also a set of unique components that are part of the Kubeflow project, like Kubeflow pipelines. Kubeflow pipelines, I haven't shown all the details, but it's very powerful because in Kubeflow pipeline, it also has experiment tracking. You can see that you could essentially, people think about Kubeflow pipeline as a machine learning pipeline, but can actually do a lot more. You can create a CI/CD pipeline.
Okay, I see it's like NIFI. NIFI is also having like this kind of flow.
Sorry?
Okay, fine, got it. So now, basically, the data, basically most of the data, what you do with historical data is all in data lake, right?
So that's a question. So I personally not
you
a fan of data
you want to
lake.
build a model. You want to build a model, and you through AI ML, and you need to run this this entire Jupyter notebook, whatever you have. Currently,
Yeah.
it's running on data lake. Now, if you
Yes
want
and no. Again, we need to understand what's a data lake. Data lakes is where you put your raw data.
Correct.
Okay.
Yeah.
You don't. Some of the things I did here, we have essentially our own high-speed cluster file system. So everything like you move really, really fast. So I click refresh and it works. So you probably have a fabric which is within the cluster for scaling the job. If you're scaling a job, you need a cluster file system because they all work on the same data. Okay. You probably don't want to go to Hadoop or S3 for running a distributed workload on the cluster. Okay. But your raw data that you're going to learn from is probably somewhere on S3 or Google Object Store. So the first step is usually pulling from an external resource. In some cases, if it's real-time data or streaming data, you will keep it on Kubernetes. You will not put it on sort of a cloud object store. And then you'll have a working set, which is probably on the cluster. You don't want to go to Hadoop for like doing joins and things like that.
Okay. All right.
Okay. I think this is part of people still think about data science. We have data lake.
Yeah, correct.
Okay,
No,
data lake
without data lake also you can do a data science, I know that. But still, if at all you want to use and exploit all the historical data to learn the model, you need to, finally you have to run everything in the data lake.
Yes, I think the other point, which is very powerful on Kubeflow, I mentioned those components. So if you go to the Kubeflow pipeline repo, you see that there are many built-in components, and some of them are sort of data lake components. Okay, like if you go to Amazon, you have EMR or Athena, which are essentially sort of a data lake. So Kubeflow does allow you to integrate with a cloud provider data lake or your own data lake. You can just create those components there.
Okay.
Okay.
Got it. Thank you.
Anyone else?
How would you compare Nucleo to the other serverless offerings on Kubernetes, like Knative and Kubeless?
So the way I position Nucleo against Knative is when someone asks me, can you compare flour, eggs, and sugar to a cake? No. Knative is essentially building blocks for building your own serverless. Okay. Is Knative equivalent to Lambda? No. Okay. That's first thing. Nucleo is a fully managed. It has APIs, SDKs. It has load balancers, orchestrators, etc. UIs, CLIs. Knative is a bunch of components. Okay, that's first thing. Second thing, I showed that Nucleo is a real-time, high-performance engine. All those things usually OpenFaaS and all those things are CGI. I call them CGI. Why? Because they're the way they work, single-threaded HTTP request response. They don't have streaming built in, they don't have checkpointing, they don't have parallelism, and Nucleo has all this notion of micro-threading inside. So Nucleo single process gets to 400,000 events per second, one process. Nucleo has things like GPU and GPU resource optimizations. It knows how to essentially take the CUDA cores and working against them. It has stateful data integration. So Nucleo is designed for data processing and machine learning. Yes, it can also do all the other things that Lambda does, but the positioning is really more around, we want to focus on, you've seen the integration around Jupyter. You don't have such a thing in any of the other serverless frameworks. So the idea is we want to take the notions of serverless, which is essentially no DevOps or minimal DevOps, automation, and all that into sort of data science and machine learning.
Thank you.
Anyone else?